Okay, so next one is the modulus of, if the modulus of a plus ai equals the modulus of 7 minus 7i, find a is element of R. A is just a real number. Find two possible values of a. Well, what we can say about a is that its modulus is the real component squared plus the imaginary component squared, which is going to be the square root of 2a squared, which is the square root of 2, and the square root of a squared, which is going to be root 2a, if we need it that way. Then it equals the modulus of 1 minus 7i, which is going to be the modulus of root 1. It's going to be modulus of 1 plus minus 7 squared, and then that's going to be root 50. Now, I was probably better off not going any further than that, because they both have square root signs. So because they both have square root signs, I can just get rid of the square root sign. So I would have got 2a squared equals 50. And then I can say that a squared equals 25, and that means that a equals 5 or minus 5. Okay, so that's very handy. So number 19 done. Now on to number 20. Now z is a plus bi. Okay, and if z minus its conjugate plus its modulus equals 17 plus 16i, find two values of z. Well, the modulus of the conjugate of z is a minus bi. The modulus of z is going to be the square root of a squared, the real part squared, plus the imaginary part squared. And then we know that all this equals 17 plus 16i, so let's find out. So what we can say here is that z is a plus bi minus the conjugate, which is minus a minus bi, plus the modulus, which is the square root of a squared plus b squared. This has to equal 17 plus 16i. Now what happens here is that the a cancels with a, and we're going to get bi plus bi, which is 2bi plus the square root of a squared plus b squared equals 17 plus 16i. Now what we're going to have here is two different equations. The first equation being 2bi ends up to be, 2b, because that's the imaginary part. 2b equals 16, b therefore is 8. And then what we can say about this then is that it's going to be a squared plus b squared, which is 8 squared, which is going to be 64, equals 17. Square both sides, and we're going to get a squared plus 64 equals 289, because 17 squared is 289 to my knowledge. Okay, and then once that's done, bring the 64 over to the other side, take away 64, and we get 225. So a squared equals 225. Square root 225, I'm pretty sure you're going to get 15. So the answer for a is going to be a equals plus or minus 15. Okay, so that is number 21 done. Now we're on to 23. Now in question 23, u is 3 plus 2i, v is 1 minus ki, where k is element r. Find two possible values of k for which the modulus of u multiplied by v is root 65. So what we got to do is we got to get u, and then we got to multiply that by v, and then we're going to get 3 multiplied by minus 3ki, and then 2i, and then it's going to be minus 2ki squared, and that's minus 2k times minus 1, which is plus 2k. Okay, and then we have to find out its modulus. So we have to find out the real part is here. So this is real, this is real. So the real part is 3 plus 2k. The imaginary part is 2 minus 3k. And that's multiplied by the I. Now remember what the modulus is. We'd get the modulus of this whole thing. So the modulus means basically the real part squared. So that's 3 plus 2k squared plus the imaginary part squared. And we're going to square this all out. Reasonably big, it's going to be that's 3 plus 2k by 3 plus 2k. So what we're going to get is 9. Then we're going to get 12k in the middle. Then we're going to get 4k squared at the end. And then with this one, we're going to get a 4. We're going to get minus 12k. We're going to get plus 9k squared at the end. And then the 12k's will cancel. And 9 plus 14 is 13. And we're going to get 13 plus 13k squared. Now 13 plus 13k squared ends up to be equal to root 65 because it says the modulus is root 65. Get rid of the modulus signs and then we're going to get 13k squared plus 13 equals 65. Bring the 65 out the other side. Oh sorry, not bring the 65 over the other side, just excuse me, it's not a quadratic. Bring the 13 over the other side and take it away. So we're going to get here is 52 divided by 13, and we're going to get k squared equals 4, and then k is square root of 4, which is plus or minus 2. Okay, that's number 23 done. And finally we're going to go on to number 24. So 24, let z equals x plus yi show that if the modulus of z minus 1 equals the modulus of z minus 2y, then 2x minus 4y plus 3 equals 0. So this is a interesting one. So what I'm going to do is I'm going to find out what z minus 1 is. Z minus 1 is basically take 1 away from the real part, so it's going to be x minus 1 plus yi. And then z minus 2y is basically taking 2 away from the imaginary part, so it's going to be y minus 2i, because you're taking 2 away from the imaginary component. Now I have to show that both moduluses are the same, so it's going to be the modulus of this one and the modulus of this one are equal to each other, so it's going to be the square root of x minus 1 squared plus y squared equals the square root of x squared plus y minus 2 squared. So look, we can get rid of the square root signs anyway because the square root signs are on both sides. So we're going to get is x squared minus 2x plus 1, that's happens when you square that out, plus y squared equals x squared plus y squared minus 4y plus 4. What happens when you square that one out? The x squareds on both sides will cancel. The y squareds on both sides will cancel, and what we're going to be left with is minus 2x on this side, so we're going to bring the 2x and the 1 across the other side, so we're going to get 0 equals plus 2x minus 1 minus 4y plus 4, and then we're going to get 0 equals 2x minus 4y plus 3. And there it is. Okay, so that's that part there. Okay.